Good evening, everyone. Am I audible? Yeah. Okay, my topic for today's presentation is Ab-Initio study on particle and lateral heterostructure of WS2 and MoS2 for gas sensing application. So my presentation starts with introduction, followed by methodology, results and discussion, and conclusion. So introduction of this topic is like we have worked on using density functional theory. It's a theoretical study on gas sensing where we have used transition metal dichalcogenides where like WS2 and MoS2 for gas sensing application, and it's a well-known material for gas sensing where we have used the technology chemiresistive method for gas sensing, and followed by this pristine material of WS2 and MoS2, we have tried to understand and analyze the sensing property of this device when we try to make the heterostructure of WS2 and MoS2. And these heterostructure are like of two types, lateral and particle, where we stack the material in particle direction. It's called particle heterostructure. And when we try to make, like, since it's a 2D material, as you are aware, so like WS2 is one layer, and after that we make the continuation of the other material MoS2, which forms a single layer on combination of both are present. So in that case, we have we try to analyze how it is affecting the gas sensing property. So in this one, we have tried like interaction of carbon monoxide, nitrogen oxide, NO2, ammonia, and H2S, and we have tried to how like sensing is like which gas is more selective towards those materials. So like as I have mentioned, we have used density functional theory. Like it's a theoretical study of for understanding the mechanism behind like gas sensing of this day. So like here I have mentioned few like parameters for like viewers, which like if you like can note down, like for like we have used cutoff value of 60 Rydberg, and like for like if is like for optimizing the first we like in this method, like theoretical calculation, we need to first optimize the material, and after that we need to like check the application part. So for optimizing the property, we need to check the how like the total energy, like minimization of the total energy, where like it's called ground state energy, where material is the most stable in the most stable form. So like for that we need to vary different parameters. Which one is the like as I have mentioned, cutoff frequency we have observed, cutoff bell energy we have observed 60 Rydberg. It could be different, like depending on the parameter we are using for unit cell and single cell layer. So similarly, other parameters are like K points and K points for like single unit cell, as well as when we try to make the single layer or multi-layer structure, there will be variation in the K point. So that also we need to optimize, and we have observed like this 4x4x1 and 8x8x1 is giving us the minimum energy. And based on once the material is optimized, we went for observing the gas sensing interaction. So like for absorption calculation, we need to first calculate the energy when no interaction is there. And after that, when we try to interact with the gas molecule and we try to calculate the total energy after that, once that subtraction of the total energy will give us what is the whether this material will get absorbed by that material. And depending on whether it is positive or negative, we need to know it is exothermic or endothermic reaction. And like we also it will give us, if depending on the value, we can identify this is more selective to us, that particular gas. Okay, so this is the like basic theory behind this work. So here I have mentioned, like as I have mentioned, we have worked on the unit cell as well as the heterostructure. So here we have worked on WS2 monolayer, where WS2 is a 2D material. We have first interacted with the WS2 monolayer, and after that, these are presentation of particle and lateral heterostructure of WS2 and MoS2. So these are some like the results I will come back later on, which we have observed, like time it, like how much time, as like you are aware, like for sensing, we need to understand how much time it takes to respond and recovery purpose. So like theoretically, we don't really calculate, like we don't able to calculate using DFT the response time, but we do can estimate the recovery of the material through DFT calculation. So these are kind of like results we have obtained. So here we can see, I have plotted all the units, pristine material as well as lateral and vertical heterostructure, like presence of different gas, how like adsorption energy is changing, and we can accordingly see the difference when pristine MOWS2 is there. So like the last one where H2S introduction is more selective as compared to any other gas. But for heterostructure, what we have observed is like introduction, like blue color is the pristine one, where like H2S selection is completely different from all other gases. So it's very clear that it will be responsive towards H2S. But for other, when it comes to heterostructure, although many reported literature suggests that heterostructure will give us a more interaction or stability, but we have observed here that interaction for all the gases are observed kind of equally or kind of less, or more or less it is almost same. So although interaction is there, but we cannot say it's particularly selective towards particular gas. So that is giving us a disadvantage in terms of like if we want to design a particular gas sensor. So like this is the observation we have observed. And after that, for checking the material is semiconducting or not, as before that, before we're proceeding, let me explain this part. Like we need to understand whether the material is semiconducting or conducting or like insulating or not. Because if it is insulating, so particularly whenever a gas interaction will happen, so there will be no variation in the structure, like we will not be observing any significant electrical variation. So if it is conducting, so like since gas molecule, we want, of course, concentration of the gas, we try to as minimum as possible, like suppose it is in ppb and ppm level. So in that case, interaction, like concentration of the gas is very less as compared to normal air. So if it is metallic in nature, the material which we are choosing, in that case, we will not, since it is already conducting, so slight variation in the conduction due to the other presence of other gas will not be differentiable to identify there is a gas. So we try to implement semiconducting material for such application where like slight variation in the conducting, we can see the difference and we can identify, yes, there is a like sensitivity towards that particular gas, and we can identify, yes, there is a detection of particular gas. So like here we have observed for WS2, it is a semiconducting in nature and it's a direct band gap material. So next, when we have tried to identify the like density of state spectra, like this gives us which generally is a wide spectrum where like we have observed only like the bands which are close to the Fermi level are more like important in terms of identifying the interaction. And here we are like in the beginning, like in the figure 4, where we have just without any interaction of any other gas, we have observed like what are the different bands present in that and of WS2. After that, when we try to interact with this, so we can see clearly the difference in the band gap is happening in presence of all the gases. So this is a identification that like this material is sensitive to all those gases. And also we can see that this DOS spectra gives us an explanation of which kind of bands, which if you have like we have studied S band, P band, D band, many bands are there. So which particular band is responsible for such interaction? So this like from density of state spectra, we can identify those things. And like for experimental purpose, when we try to implement this, so we can modulate in that particular area where like as per our requirement of the work. So like this is theoretical analysis helps us in identifying those parameters. So next, as I have mentioned earlier also, like heterostructure of vertical and lateral heterostructure we have tried. And there we have seen that this, as we have seen in the previous slide, WS2 is a semiconducting in nature. But once we have made it a lateral and vertical heterostructure, this complete structure, like there is no band gap in that material, like in this material. So like although both MOS2 and WS2 both are semiconducting in the pristine form. So it signifies that formation of the heterostructure has significant change in the material property. So in this case, like as you have seen, so if I like do some interaction of the different gas, so we may not be able to, although there is an interaction, but we may not be able to identify the particular gas has a response towards that particular gas material. So like last is the conclusion slide. As I have mentioned, we have worked on theoretical study on gas sensing of carbon monoxide and nitrogen and various toxic gases, which on WS2, pristine monolayer, and its heterostructure with MoS2, where we have observed this pristine WS2 material is more selective towards H2S gas, and it is not that much interactive to other material, other toxic gases. But in case of heterostructure, we have observed that there is a interaction is there, but we may not be able to identify, or you don't see the selectivity towards particular gas. So from this study also we can observe, as we have seen, we have made a particular type of lateral heterostructure and vertical heterostructure. So vertical, there is a gap between these two. So based on that also, which we will try later on. This is a small work. So depending on the gap between these two also have impact on that. And similarly, laterally, the way we want to calculate, optimize the device, that also has an impact on analyzing or modeling such things. So this all from my side. Thank you very much for listening.